Good evening and welcome to Sherwood Observatory. I'm just going to say a few words about the observatory before handing over to the rest of the team. So Sherwood Observatory was built 50 years ago this year by members of Mansfield and Sutton Astronomical Society. We've got a large telescope, which you can see on our website at sherwood-observatory.org.uk. What we normally do is host visits here for the Cubs and Scouts and Brownies and guides. You can come here and you can earn your astronomy and your space badges. But at the moment, we're not open. We're hoping to open again soon. So if you watch this space and keep an eye on the website, then we'll let you know in the next few weeks when we're open for business again. And then you can come along and see the observatory, get to use our telescopes and learn about what we do here. So I'll hand over to the rest of the team now when we get into the event proper.
Hello, my name is Kerry Morrison. I'm a lecturer at Loughborough University. I've been asked to speak to you today. So just to give you an idea of my background, I actually grew up in London. Didn't really think that I was going to do physics when I was probably around about your age. So I was more interested in mathematics and just tinkering around with things. I really liked chemistry, biology, physics, all of it. And I made the decision to go into physics somewhere towards very close to actually going to university. So at the time, I was very good at math, but I hated physics. I know this sounds terrible. I hated physics because it was learn these equations and apply them in some way. And to me, I could see no point to doing that, and it was completely disconnected from the maths as well. But one of my teachers, they turned around and they said, you know what, if you go to university, physics is more about math. You actually, it's really beautiful. You get to see how you can use mathematics to describe the world, and that's part of the reason that I ended up choosing it in the end. The other part is I was lucky enough to be invited to do an open day at Imperial College, where I actually ended up going. And they had this demonstration. So to entice you into physics, they had this demonstration, which was with a superconductor, and I still remember this. So I must have been about 17. As a 17-year-old, I got to play with liquid nitrogen and some giant magnets, and probably wouldn't be able to do it now, and a block of superconductor. And the idea there is you get this magic material, you cool it down enough, so you put it in the liquid nitrogen, which just has like clouds coming off of it. And then when you place it near a magnet, it starts to float. And one way or another, that really inspired me to go to university. And eventually it inspired my choice of PhD. So I actually did a PhD in superconductivity and magnetism. In practice, it meant I was looking at a lot of magnetic type materials, and this will sound weird, to be able to use them to build fridges. So the take-home message that my grandparents always took from that is that I did something with fridge magnets. I didn't, but it was close enough. And that was really kind of inspired just by this one demo that I got to be involved with. So what I do now as a lecturer is still quite similar. I'm still looking at magnetic materials, but I'm more interested in how I can use them in other ways. So my current research interest is, can I use what I know about magnets, these special magnetic materials, and can I make a device that can convert waste heat into useful energy? That's one of the current projects that I'm working on. I think that's about me for now. So I'm going to hand you over to Kerry. I'm going to disappear for a bit. It'll be blank because we're having to socially distance, but I swear she's coming.
Yeah, wonderful.
Hello, my name's Kerry Wharton, and I've just graduated from Nottingham Trent University with my degree in physics. I'm going to be carrying on forward there to do a master's degree in medical imaging. So I've always, when I was quite young, I didn't want to go into physics. I wanted to be a doctor. However, I was then not very good at biology and was a lot better at maths. So I ended up leaning more towards physics and then really getting into sort of the imaging process. So like in hospitals, when you want to look at x-rays, I loved looking at like all the different ways you can look inside the body. I loved seeing all the different, I loved anatomy at that point. And actually what ended up happening is I did not do well in my physics exams, and I actually went on to do a art foundation degree instead, because I thought that was the most, you know, it was going to be the best use of whatever skills I had. And I ended up, I think I probably did 2 weeks into that degree before realizing I just really liked physics, and it's just I needed to work harder. I needed to put more effort in to then be able to get to go where I wanted. So I ended up stopping my foundation degree. I went back to my sixth form to redo my A-levels, so then I could go on to physics, and I was lucky enough to get a place at Nottingham-Trent University, where like it was very difficult. Like it's not that I'm not smart, but I was sometimes slow at grasping concepts. So then, like, with the help of the staff there, like, I was eventually able to build up my confidence, and that's the only reason I managed to get to where I am now. Like, once you don't necessarily have to be like the smartest person in the room to then go on to do physics. It's just you've got to sort of put the effort in. So now I'm looking to hopefully carry on there with the master's degree. And I don't actually know where I want to go yet. I'm still sort of stuck, but hopefully it's going to start guiding me in a direction that I think will be really good for my future. Right, thank you.
David says it's got your slideshow. If you want to show that.
I couldn't. It's talking about neutrons.
Can you see some questions?
Yeah.
I want to say if anyone wants to ask any questions about the observatory as well.
Just walk back and forth. Yeah.
Okay, so Kelly and Kerry have introduced themselves, said a little bit about their background. So if anybody has any questions about the observatory or just about physics in general, or to ask Kerry and Kelly anything about what anything about physics, about their journey into physics, about what inspired them in physics, then just there's a questions thing within the webinar where you can type in a question. So I have a question coming already. So there's one question here, just to Kelly. That's okay. So can we try and get Kelly on the screen? There we go. So should we point it? Okay. So they were intrigued to know about how old you were when you changed your mind about, because you both did this, right? Going from not liking physics to actually, I like physics. So how old were you? When
I was 18.
You were 18?
Yeah, I put in, my UCAS options were chemical engineering, mechanical engineering, all very applied, and physics. Oh, there was one for natural sciences as well, so that could have gone anywhere. And I didn't decide until I accepted the offer. My birthday's in December, so I must have been 18 by the time I said yes, decided something. Why not?
Okay, great, thank you. And so 18 and you changed. So actually a kind of similar question away for Kerry. So do you want to just jump in? So again, about you started doing art.
Yes.
So you clearly enjoyed art. Do you still do any art?
Yeah, I still do like fan-made graphic design posters for like movies and TV shows and things like that. And then I do a lot of nature photography outside of that. So yeah, art is still a very big part of what I do.
Yeah, good question. So you think having an arty perspective helps with physics, seeing things and understanding things?
Definitely. like I really struggle with concepts that, like concepts of infinity, because I can't sort of visualize them in my head. But then like if you look at sort of mechanics and the way things move, I find it a lot easier to understand because I can sort of visualize things a lot better because they're just more realistic in a sense, and they can just picture them, and it helps me. It's really good for figuring out how things are moving around.
Great, thank you. So history and art background can be helpful when you're a physicist as well. So it's not science or art, you can do both, and they're useful. Okay, a question for Kerry, please.
I want to just put this back in the middle.
Yeah, sure.
There we go. Okay.
Yep.
About floating, so how does that work?
Okay, there's something called the Meissner effect. So it's the best way to explain it is to start off by saying how a superconductor is defined. So a superconductor itself is in the name. It has zero resistance. So that's the first property you look for. Like you could pass a load of current through it, and it's not going to heat up like electrical circuits normally would because it has zero resistance. It'd be great for power networks, for example. Now, a second observation that they've made for superconductors is something called the Meissner effect. And this is it's basically a perfect, what we call a diamagnet. If you expose it to, put it in a magnetic field, it actually generates these little currents on the edges that creates its own kind of opposite field. So it's like you've got two forces pushing against one another. This is the magnetic field that it sees, and this is the magnetic field that it generates, and that will oppose gravity and help it to float above the magnet. I'll try to.
Okay, yeah, great. Complicated effect, isn't it?
It can be quite complicated.
Yeah.
There are loads of very, very complicated theories to explain what's going on. Usually it's much easier. If you ever have a chance and you've got the community day at Loughborough, I normally have a superconducting train demo, so you've basically got it floating along the track. And then when you see it, you can actually explain a lot of the things that are going on just by, I like playing with things because I'm not visual. I like to have someone in my, like that I work with who is visual because I can't understand what things look like, but if I can touch it and play with it, then it's a lot easier for me to grasp.
And you said you have a community day at the university.
Yeah, every year during British Science Week. Obviously there are issues with the current situation, but every year during British Science Week, Loughborough University, they open up the campus on a Saturday usually, and there's loads of different sciencey things that you can do. I've been doing stuff for the last 5 or 6 years. The last 2 or 3 years has been nitrogen ice cream, and before that there's always been the floating train demo because I love it so much. I like playing with nitrogen.
And is it safe?
No. You may have seen it in some TV shows or films. So liquid nitrogen is very, very, very cold. You can burn yourself just like you can burn yourself on a hot stove because it's so cold, and it's extremely dangerous if you should never drink it. Because it's so cold and it's in a liquid state. As soon as it warms up, it kind of expands into a gas, and it takes up 70 times more space than it would as a liquid. So obviously, if you drink it, things are going to kind of go bad. So never do that. And you can burn yourself. However, everything that you do in a lab, there are usually risks involved. If you use lasers, for example, if they're too strong, they could blind you. If you use high power electrical equipment, if there's a short circuit, you could get an electric shock. But the first thing that you do before you even go into the lab is you find ways to minimize those risks. So with liquid nitrogen, it's one, obviously you're not going to drink it. That's pretty easy. And the second one is you wear what we call PPE, personal protective equipment. So a mask is a good example of that at the moment, I guess. The liquid nitrogen, that would be special kind of gloves that keep your hands insulated from it. And if you're handling if you're picking something up from it, you would use tongs, so big tweezers, to pick whatever you plopped in there out and put it somewhere safe. So you're sensible with it and you're fine. It is dangerous, but seriously, I've used it for 15 years now and not been burnt or hurt myself in any way.
Okay, and another question to both of you, really. You both mentioned that you're quite good at maths, and that helps the physics. What if you're not good at maths? Can you still do okay at physics?
I mean, I was never like naturally good at maths. I had to put a lot of work into my maths. So say in my first year at university, you would normally do one maths module to help you cover the end 2 years. I had that and then 2 additional classes that I went to help me get better at the maths, because I was just not able to keep up with everyone else. So I definitely had to put a lot more time in because I wasn't good at maths. But then I still came out with a degree in physics. So you can definitely not be good at maths and still be able to do physics.
Great, thank you.
Okay. And from my viewpoint, so I lecture different courses. There is a lot of maths content. You can't get away from that. And usually at the university, there is a lot of support for that as well. And what you do find with the physics degrees, it's quite common for it to split. You can do theoretical physics, which is so much math, and you can do applied or core physics, which is kind of the bare minimum that you would need to understand everything else that you're going to talk about. And by the time, if you're to do a 4-year course, for example, at Loughborough, so the one course I do teach, if you got to the 4th year and you're in my module, if I'm teaching you, the amount of maths that you actually need to know is very, very, very minimal, because for that course at least, I'm more interested in different measurement techniques that you can use to understand the world or materials. And so there's some math to help the student intuitively understand what they might see. So I get them to describe mathematically diffraction, for example, so some optical effects, and then we use the solutions for that to describe in a more generic way a whole host of other types of measurements and how they work. There's the way that you get graded on that module is largely, can you understand this research paper that I've given you? Can you design an experiment and justify what you're going to do and how you're going to do it? And these tend to be what we call soft skills, which I think are very important and kind of undersold sometimes. But as far as working on very large kind of research projects, they're extremely important. There's no way that you could coordinate, for example, someone going into space if someone didn't sit down at one point and think, well, if I do this, then I have to do this step, and then I have to do this step, and I need this kind of equipment or measurements or data to be able to do that. So there has to be some planning at some point that understands what's going on at the same time. So it's not all maths.
Yeah, great, thank you. So just to point out, if anybody else wants to ask some questions, you should find at the top right-hand corner of your screen. So if you expand on that, there should be a little box that says questions in chat. So if anybody out there wants to ask Kerry or Kerry some questions, anyone else wants to ask some questions, please do so. They'd be delighted. And actually, you can ask Steve some questions, anything about the observatory too. If you see anything in the background that you might think, hey, what are those things in the background? Stick a question in there, and we will try our best to answer them. So that's kind of why we're here, is to meet a physicist and to chat to physicists. So let me have a little look. What else do we have here? So please, yeah, type in something. Okay, so here's a question for Kerry, please, if that's okay. Well, Kelly can answer this afterwards as well, actually. But so, what was your favourite bit of physics, both at school and at uni?
So at school, I really liked like mechanics and forces. So I liked sort of how things moved and how things worked. So I really, for a long period of time, my main focus in physics was like, I wanted to do something like engineering based. I wanted to use sort of those skills. Then as I got to uni, I still really enjoyed those elements, but then I was introduced more in depth to medical imaging procedures, so like x-rays and MRI scans, and they really piqued my interest. I think going back to when I was younger, I wanted to be a doctor, I wanted to help people. That was sort of like, okay, these skills that I have, I can use towards that goal and be able to still sort of do what I wanted to do as a young girl, but in sort of a way that I hadn't really anticipated.
Great, thank you. So same question to Kelly as well. So favourite topic at physics at school and then at uni, or
Yeah, slightly off all there, right? So again, harping back to the fact that I didn't like physics at school, my favourite physics topic was quantum physics. So Schrodinger's cat, the idea that it's not a very nice experiment, but it's a thought experiment, so it's fine. It's not real. This thought experiment that Schrodinger came up with, that you have these two boxes and you have a cat. No, you just have one box, sorry. You have one box and you have a cat in it with a bit of radioactive material. And unless you open the box, there's a bunch of other details that I'm skipping out, but unless you open the box, you don't know whether or not the cat is alive or dead because of the way that radioactive material behaves. You have, it's this idea that you have, they call it a superposition of states. So the cat is both alive and dead because no one's observed what's happened. It's very weird. Quantum physics is super weird. And when I was at school, most of the physics that I found interesting was the stuff that wasn't on my curriculum. So they taught lots of mechanics. They didn't teach any quantum physics. I think they do now. I think they've added to our knowledge. So I was just reading popular science, and really there's nothing wrong with that. I think that's generally what can get a lot of people interested in it. So there was this author whose first name I've forgotten, but surname was Gibbons, and I read so many of his books, and they were talking about the same thing: quantum physics, wave particle duality, all of these really spooky things that happen. And even when you get to university, you don't fully understand. If you think you understand it, then you don't. But when I got to university, I still enjoyed doing the courses on that and understanding it. But my favourite course was actually in the lab. So I liked, again, being able to do things hand-on, to play around with different bits of equipment, to observe what the result of that was, and then to plan the next step. So it's not quite a subject that covers everything.
great, thank you, thank you. And so let me just check a couple more questions coming in. Here's one from Tracy. Maybe to Kelly again. What's the most dangerous experiment you've ever done?
Okay. So there are experiments I go on that require using neutrons. Now, neutrons are technically radioactive particles. I use them. I basically, you can imagine that they're like balls. I will bounce these off of the surface and it will tell me stuff about a very thin film that I'm looking at. But because they're radioactive, technically you're putting yourself at quite high risk when you go and do these experiments. So there's this reactor in France, in Grenoble, that it's an active reactor. So they have a radioactive source and they're generating neutrons from this, and then kind of guiding them to what we call experiment chambers. So they're guiding these neutrons in. And because you have to walk into this hall, there's a lot of shielding so that you're safe to an extent. But because you have to walk into this hall, you have what's called an active dosimeter. So that measures how many neutrons you're being exposed to. So you can actually be sitting there doing your experiment and it will go beep, and it'll tell you that you've seen a neutron. There's a limit to how many you can see in a year, and it's heavily regulated. But as part of that, you're actively being monitored. And then on the way out, you go through this really cool machine. So first off, you have to go through an airlock because there might be radioactive materials. The whole, you have this kind of positive pressure between the outside world and where you've come from. So you go through this airlock and it kind of changes the air before you then move on to the safer part. And then you go through this machine where you basically put your hands like up and down, so it can check that you've not inadvertently got some radioactive material on your hands and you're bringing them outside to the outside world. Because with these experiments, I should have mentioned as well, just by putting my material, my sample in this neutron beamline, I can make it radioactive. So it would be, if I was not careful, it would be very easy to make that radioactive, touch it, touch my face, walk outside, contaminate a whole bunch of things. Exactly the same concern that you might have with COVID at the moment, where you're thinking about transfer of stuff. So the ways that they get around that is your dosimeter, and then on the way out, it checks your hands, and then it checks your whole body, ticks you off, and then you can kind of go and have lunch.
So, Kerry, to you as well. I don't know whether you've done any dangerous experiments you want to tell us about.
I don't know that I'd say dangerous, but I remember the scariest one that I did. I was being trained to use the MRI machine at the university, and probably won't name any names because I don't know that I was supposed to be left alone. But I was basically that we put a sample in the machine. Basically, this person went, "Do what you want for half an hour. I'm going to go away." And I was just left alone with this really expensive piece of equipment that I.
How expensive?
Oh, I don't. Is it 7 million? Several million. So, and I was just left running about, playing with it, doing what I wanted, and I was like, it was terrifying. So I was like, oh my god, what if I break this machine? I'm going to be in so much trouble. I can't afford to replace this. So that was probably the scariest thing I did in physics. Maybe not so much danger.
But nothing went wrong. It was okay. It was okay.
Everything's still running. I'm not in trouble.
Okay, Tracy has a question for Kelly about metal that is not magnetic.
Yes. Wait. Oh, that's a difficult question. That could be a difficult question. Okay. So when you talk about magnetism, you can classify it in different ways. So what we know as a fridge magnet is what we call a ferromagnet. So it's very magnetic. You can pick up different types of metals with it. So, you know, pins. You can get other, so the superconductor that I talked about, that's a type of diamagnet. So it sees a magnetic field and it behaves in an opposite way. It's awkward. And then you can get something called a paramagnet. So this is something that you can check on Google later, or YouTube, sorry. So a paramagnet is something that you apply a magnetic field, and it does respond. So it's ever so weakly magnetic, but really not at all. So if I was going to say something's not magnetic, I would say it's a paramagnet. And a lot of materials are like that, really. Anything that's got water in it, though, tends to be diamagnetic. This is the thing you can check on YouTube. And then if it is diamagnetic, then you put it in a large enough magnetic field and it will float. So there's these brilliant videos of floating raspberries. With Nottingham, not NTU, sorry, but with Nottingham University, they've got videos of floating water droplets in a magnetic field as well, where they kind of get to spin around. I could talk about frogs, but I'm not going to.
Okay, excellent, great. Which, take it in turns, this one. So who is your favourite female physicist?
Oh, alive or dead?
I don't know, well, either, yeah. So, or scientist, if you want to. So your favourite female scientist?
Oh, I'm blanking on the name.
I think there's some in the background there as well. No.
Mind,
Have you? Okay.
So sorry, I'm going to put you on the spot.
Oh, do you want to say?
Yeah.
So actually, so Steve has a reply to this one. Yeah, go ahead.
Right. Okay. So I have a famous scientist, Dame Jocelyn Burnell. So she was the lady who was working in astronomy, so really a physicist, I guess she probably is as well. And back in the 1960s, she was the first person to discover pulsars. So these old, nearly dead stars that are rotating very quickly. And she was doing some experiments for her PhD, and she identified this effectively like a lighthouse in the sky, and her PhD supervisor wouldn't believe that she'd discovered an astronomical object. He thought it was something in the university where she was working, but eventually she convinced him, and it's been described as one of the most significant scientific discoveries of the last 100 years. So that's Dame Jocelyn Bell Burnell, and she's actually been to this observatory and given a talk to the members of the observatory and some children from local schools who also came along. So she would get my vote.
Yeah, thanks, Steve. She's a wonderful scientist for sure. She's actually giving a talk with the Institute of Physics as well. So I'll plug it quickly. So I forget the date now, but later in the winter she'll be talking. So if you fancy listening to her, and she's definitely alive to give that talk. Prize recently, you should donate a lot of the funds to pay for students from female students or underrepresented students to go and study for really wonderful millions of pounds. So she's really inspirational figure. We're just giving some time for Kelly and Kerry to think. So do you,
I remembered that.
Okay, Kelly's remembered the name. So yeah, go ahead.
Sorry. So I would say most inspiring what I would classify as a physicist, although you could argue over this, is Rosalind Franklin, because as far as I'm concerned, she's the one who interpreted the X-ray diffraction data of DNA that Crick and Watson were trying to figure out. They were really excited. They did a measurement, but they didn't actually really know much about X-ray diffraction to be able to interpret it. She was the one who did the measurements, and she had this huge background in it and managed to really figure out what the structure was. And it would have been incredibly complex without being able to use computers, for example, to help you. So a lot of kind of looking at photos and figuring out the patterns in them, and then from the patterns building this real image of what it looks like. It would have been a huge challenge. So I have so much respect for her that she managed to do that. And you know, if you know enough history that Crick and Watson would have won the Nobel Prize, the only reason I believe that she didn't is that unfortunately she passed away from cancer before it was awarded, and they won't award a Nobel Prize to someone who's already passed away.
Great, thank you. Just to so the Jocelyn Bell Burnell's talk is on the 12th of November. I've never been reminded of the date, so if anyone fancies it, we'll be posting details of that. She, Steve said, is another great living British, I think Northern Irish actually. Is that where she's from? I think. Yeah, so Northern Irish physicist. I think Kerry's remembered her name too. So here you go. Yeah, go on over to you, Kerry too.
This is either where I get the name wrong or I pronounce it wrong. But so it's, again, I think more inspired. So when I got the title, because it was just like something I maybe hadn't done before and didn't really understand, and it was basically to develop a like smaller MRI machine to look. The study they were looking at was to look at the placenta in a pregnant lady. So I ended up reading a lot of Penny Gowland's papers, and I believe she's from the University of Nottingham, on placental MRI, and that is when she actually made me really look forward to my project. I think making me sort of understand the goal that I was aiming for with it, rather than just looking, here are the signals that I'm going to get, and that's it. I think reading those papers and then seeing the end goal of what I'm maybe going to be able to achieve really pushed me to then do what I could in my project. So I think more of an inspiration than,
Actually, someone is intrigued about what are the things we can see in the background behind the camera. So I don't know whether Steve wants to just go and give a little. There are some sort of artifacts and exhibits and things. So
okay, I
yeah,
may have to do a little bit of roving here with the laptop if I'm allowed to move it. So apologies for the jerky screen. So hopefully you can see this. So this is one of our small telescopes that we have here at the observatory. We also have a very large telescope upstairs in the main dome of the observatory that's about the size of a small car and weighs about the same weight as a small car. So if you come to the observatory, you can actually have a go at using these telescopes, and you can also get to look through and play with the large one upstairs. So the way this one works is that I'll just put the laptop back down again so it doesn't shake too much. But the way this one works is that the light comes in through the top end here, goes down to the bottom, reflects off another mirror, goes up to the top, and then back down again and comes out, and you look through an eyepiece here. Now the good thing about this telescope is it's got a sat nav, like you get a sat nav in a car. So once you've got it set up and you've got it pointing at the sky, you can just press the controller, a little hand pad, and name any object in the night sky that you want, and the telescope will automatically turn around to it and point at that object and stay on that object for the rest of the evening. So if I want to look at Pluto, that would be a bit difficult to find with this because it's not really big enough. But if I want to look at, say, something like Jupiter, then it will automatically swing round to Jupiter, and we can see the cloud patterns on Jupiter. We can see the 4 Galilean Jupiter moons. If we turn it to Saturn, then we'll get a view of the rings of Saturn, and you can even see some of the gaps in the rings. Bigger telescopes are better, so that's why we sometimes use the very large telescope upstairs, which is much, much larger than this. So this has got the mirror's 20 centimeters in diameter on this one. The one upstairs is 69 centimeters in diameter, so it's much bigger. And that means you gather much more light, so you can see fainter objects. Yes, that's right. Some hand gestures going on in the background. That is how big the mirror is. Yeah. In terms of some of the other stuff, I'll just move the telescope out of the way. They're quite heavy, these telescopes. We have my friend Buzz Aldrin here in the background. See, I'm taller than Buzz Aldrin, so I wouldn't make a very good astronaut. So Buzz Aldrin was the second person on the moon, and the reason why we have a cardboard cutout of Buzz Aldrin is because last year was the 50th anniversary of the first moon landings. Incidentally, that's one of the things that got me into being a scientist, because I was just a young kid when that was happening. And we did a big exhibition at Mansfield Museum last year to celebrate the 50th anniversary. And so we had Buzz here, and some of the other posters that you can see in the background we also had up at the museum as well. So we're actually standing in the lecture room of our observatory at the moment. So if you do get a chance to come along when we open again, this is where we'll bring you in. We'll show you some cool stuff about the night sky.
Thanks, Steve. Pointing out that post has made me realise that there's a few other women in space there. So I don't know whether you want to just say a word about one or two of them too. So some other women in space. We can see.
Yeah, I'm not quite sure how close that's coming out. There was a great film just came out a couple of years ago called Hidden Figures. It was about the women who were involved in the space race. Because if you look at all the old stuff about NASA in the 1960s and early 1970s when they were doing all the moon landings, you'd be forgiven for thinking that there weren't any women involved. Well, at that time we didn't have women astronauts, but there were women in the background who were basically doing all the hard maths and physics that was getting the astronauts safely to the moon and back again. And this poster here just shows some of those who were really working in the background and didn't get the recognition they deserved until a couple of years ago when, like I say, the film called Hidden Figures came out. So if you get a chance to watch it, watch that film. I'd really recommend it. The bottom two figures are a couple of female astronauts. So the first one is Valentina Tereshkova. So this one here was the first woman in space, Russian. And the bottom one is the first British astronaut. A lot of people think that was Tim Peake, but it wasn't. It was actually Helen Sharman. And Helen Sharman comes from Sheffield. Right. Excellent. I'll just put this back up again.
Yeah, great. Thank you, Steve. I think when you were talking before, Irene asked about whether, I think as you were talking about telescope. So yeah, that is a telescope, but it maybe doesn't look like what you typically think a telescope should look like. It's really short, isn't it? So Steve's got another one here, which maybe Irene is more like.
So So this is probably more like what you imagine a telescope to look like. The problem is with telescopes, as they get bigger and bigger, they get longer and longer, so they get quite hard to use. So the reason why this telescope is very short is because the light goes up and down the telescope a couple of times. So there's mirrors inside of it that bounce the light around, and that means it's nice and short and compact and easier to use.
Oh. Yeah, good question. Yeah, because they really don't look like telescopes. They look like drums, don't they, really? So, yeah.
You want a slightly bigger one?
Oh,
hang on.
There's another one.
We've got lots of telescopes. That's what you got to observe. Lots of telescopes. We've got this slightly bigger one here. Oops. I just took it forward. We use this one at our exhibition at Mansfield Museum. So we've cut lots of holes in it. You can see the holes here. And get my hands in so that people can look inside it and you can see how a telescope actually works.
Great, thank you. And one from Tracy here, which she's asking, have you ever tried to find the sun at night with the telescope?
Right, lots of questions for me now. Well, we can't do that because at night the sun has set, so it's below the horizon, so you wouldn't be able to see it from here. So when the sun's set here, so for example, the sun sets in the west, so after dark here, if you were in America, because America's 5 hours further around the Earth, it would still be light in America, so you'd be able to see the sun there. What we do have at the observatory, those special telescopes where we can look directly at the sun and see lots of detail on the sun. Now, the health warning is you must never look directly at the sun with your eyes or with any sort of telescope or with binoculars, because you'll go blind before you have a chance to take your eyes away. But we have some very specially adapted telescopes here that filter down the light by something like 99.999%, I think it is, something like that. So we can look safely at the sun during the daytime when it's not cloudy, of course. And when we do that, we can see things called sunspots, which are slightly cooler areas on the surface of the sun, and we can see solar flares. And when we look at flares on the edge of the sun, they look like little flames coming off the surface of the sun. And the sun's so big, we have to keep reminding ourselves that those little flames are actually much, much bigger than the Earth. So yeah, there's some really cool stuff to see on the sun, but I'll say the warning again, only ever do it with specialist equipment like we've got at the observatory.
Great, thank you. Yeah, good questions. Charlotte, I think I missed this. So let's ask it again. This will be from both Kelly and Kerry. How much do you like maths? So on a scale of, I don't know, so yeah.
So it's not that I don't like maths, but it's definitely not my favorite element. So I'll do it, but I probably won't be happy about it. So I'll get on with it. Like it's, you know, can work through it. There are some people that like really enjoy it, and that means they'll go into like a different area. I think maybe just because I'm not the best at it, I'm not a massive fan of maths, but you know, there's very little you can do without it. So
Teamwork.
yeah, so if I always work with someone who's better at maths, especially in like a lab environment, you know, I'm good. I can get all the measurements and things, and then I'll just hand it off. They can deal with the maths problems, so I don't necessarily have to.
Okay, like I said earlier, I really liked maths as a kid. It was my favourite subject.
Did you like it more than ice cream?
Probably.
Oh, oh.
No. I never got the good ice cream. There's always that really cheap kind of watery stuff, so I wouldn't have known. Anyway,
Maths is better than cheap ice cream.
Maths is definitely better than cheap
Right,
ice
okay,
cream.
okay.
I definitely now, if there's a choice between ice cream and maths, I'd go for the ice cream. But yeah, now it of course, I'm what you call an experimental physicist, so my job is to be a physicist. I do lecture as well. I do not use that much heavy maths on a day-to-day basis. So I may do some trigonometry, which you'd get to at some point, I think, during the GCSE. So So I might use that routinely just to figure something out in the experiment that I'm doing, but I don't actually do that much difficult maths. And even when you get to the point, at least in my field, where you are possibly having to do the difficult maths, we're now at a stage where you no longer need the human computers that they needed for the space race. You have physical computers. So as long as you can write a computer program to do the maths for you, you're fine, basically.
Okay, so one likes that maths and one doesn't like maths. So yeah, teamwork. People can work together and all those computer programs. Tracy has a question about which nation is Tim Peake from. So maybe we're surprised to hear that Tim Peake wasn't the first British astronaut.
Okay, well, yeah, Tim Peake is British. He just wasn't the first British astronaut. So, yeah, still a big fan though. I was just pointing out that Helen Sharman was the first astronaut. So if you're listening, Tim, I meant no offense.
Okay. So there's a question for Kerry again about the art. So we asked previously, are you still doing some art? Do you still like art? Do you go to galleries? Do you, I don't know, do you enjoy art?
I still really enjoy art. Like I do, especially over lockdown. I've spent like a lot of my spare time just, I could doodle for hours, just build up anything. I love making like posters for like superhero films, so like the promotional posters you'd see. For years I wanted to do that, so I'll make like a lot of those at home. I don't make as much time for the galleries as I used to. I think I never really enjoyed traditional art that much. I did a lot with like digital and computer based, so a lot of the stuff I'd look at online anyway. So I still do go through like a lot of different artist pages and, you know, look at their work, see what I can bring into mine. So it is still definitely a big part of what I do, and I think, yeah, it has been really helpful.
So what we might do now actually is we think the Wi-Fi is going to be good enough to go for a little walking tour around the observatory. We go see the big telescope, the one that really does look like a telescope, right? So yeah, there's no other questions on the chat, so I thought we'll maybe do that. Okay, so we'll take the camera. Yeah.
Okay, so this is kind of gonna look a bit Blair Witch, but we'll see what we can do. Okay, if we lose the Wi-Fi, we'll reconnect again in a moment. So just bear with me. So where we're going now is just up the stairs, and so we'll go up some stairs here. It will be a little bit dark, so the picture might not be so great. And I'll then set up the I don't know if we're going to be able to see this. Yeah, I'll set up the camera there so that you can see the telescope and get an idea of scale. So it's so big you can't even get the whole thing in. So if I go and stand beside it, you'll now get an idea of the scale of the whole telescope. Now, this telescope was built by our members, so it's built out of recycled materials. So these bars that you see here, the telescope's made of, are scaffolding poles that you see on the outside of buildings when they're being built. So when the observatory was built, the members reused the scaffolding poles and welded them together to make the telescope. Sorry, it's a little bit dark in here because we normally don't have much light, and we've got the power off, so that's not quite going to work. Sorry, we're moving around. The telescope is on this big U-shaped thing here in blue, where we can control the height of the telescope up and down. So if an object's high in the sky, we can raise the telescope, and it rotates around that axis. So if something's moving across the sky or there's a different place in the sky, we can turn the telescope to it. Now, they were still recycling when they built it, and they didn't have any money. So the main axis that turns the telescope is actually the back axle of an old lorry. And it's now all computer controlled, like the little one downstairs. So again, we can just go to the computer screen. Sorry,
Apparently we've lost the Wi-Fi.
oh. Okay, yeah, we're probably in the limited
Weird.
Let's see if it.
Yeah, so you might have dropped out of the Wi-Fi there. So that's our telescope, and as I say, well, possibly the other thing to point out, you might not see it in the background, we can see some big step ladders there, and the reason for that is that the eyepiece of the telescope, where you look through, is right up there at the top of the telescope. It's actually on the other side of the telescope. So when we're pointing the telescope high in the sky, you have to climb up those step ladders over here in the background, so that you can get your eye up to where the eyepieces of the telescope is and look through it. So as I say, keep your eye on the website, and when we open again, you'll get a chance to come up here and play with our telescope. Oops.
The question about, have you ever seen a shooting star?
Yes. Well, I'll come back downstairs and answer that so we don't lose the Wi-Fi.
I wanted to kind of show from outside too, just to show the dome.
Yeah, we might lose the Wi-Fi from the outside there. I'll answer the shooting star question in a moment, but let's have a look at the outside. It's getting very complicated. So if we go over here, there you are. You can see the dome of the observatory in the background, and that slightly wider bit that you can see opened, and then we can point the telescope through the dome. So the whole dome will rotate around depending on whereabouts in the sky we're looking. So, I've never done a walking presentation before, so bear with me. It is really much easier when you can actually visit in person and we can walk people around. So yes, the shooting star question. Yes, it's actually quite easy to see shooting stars. So shooting stars are small particles that burn up in the atmosphere and they produce a bright light as they're burning up. There are meteor showers like the Perseids and the Geminids at certain times of the year, and they're your best chance to see them. And anyone can see them. You don't need a telescope. So if you just go out on a clear night when there's a meteor shower happening, you can find out when they are by looking on the internet. Go to a dark place, so that could be your back garden if you can switch the lights off. It takes about 20 minutes for your eyes to get used to the dark, and then just sit in a chair or lie on the grass if it's a warm night and just look up at the sky, and then every so often you'll see a shooting star. Here at the observatory, we actually have a radio astronomy section where we can detect shooting stars coming in even if it's cloudy. So that's another thing we do here at the observatory actually. Okay.
Okay, yeah, wonderful, thank you. Yeah, so hopefully you managed to stay with us for that little walking tour of the observatory. Clearly much better in person if you do live nearby, and when restrictions are released, be great for you to come and visit. If you don't live nearby, then there are other observatories around the country. Be really good, great place to take your groups to. Just seeing if there's any more. Got a minute or two left, but if not, maybe just a farewell from everybody. So just saying thank you to Steve, and to Kelly, and to Kerry, and to me. Thank you all for listening. We hope you've learned some physics, met some physicists. I hope to meet you in person sometime soon. Okay, bye.